Okay, as people find their seats and hopefully our power is restored soon on this side for laptops, I'd just like to introduce you to this session. So this is the EnviroSensing cluster session for summer 2019 here at ESIP. We're really glad to see the room filling up. We still have a few seats up over here on this side if you want to be closer and see some of the tiny fonts we're going to project on the screen for you. I'm Scotty Strachan, so I'm from the University of Nevada, Reno. I'm a director of cyber infrastructure in the Office of Information Technology. I'm also director of a sensor network that spans our state and 3 institutions. So the Nevada Climate Eco-Hydrological Assessment Network, NEVCANT, and it was actually science and eco-hydrology that brought me into the orbit of this cluster and this topic. Many years ago when Don Henshaw and Corinna Grias were leading this cluster and starting the best practices work for EnviroSensing. They were very kind to bring me into the community, and that's where I met Renee and several of the other folks that are in this room actually. And I found this community to be very welcoming and inclusive. And those of you who are first timers, I know we have a lot of first timers to this meeting. Our cluster is also very open. If you're interested in any of the topics that we're gonna go through, both in these presentations and that we cover over the course of the year, feel free. We're gonna actually pass around a sign-up sheet. Feel free to add yourself to the email here. We can put you on the listserv if you're not there already. So I'm gonna start passing this around.
And while test.
It might take a second to boot. I just turned it off so it wouldn't feedback. There we go. Yep.
Test. So I'm Renee Brown. I'm the co-chair of this session or cluster, I guess. I work at the University of New Mexico where I'm the information manager for the McMurdo Dry Valley's long-term ecological research site. I'll be giving a talk about that later in this session. I'm also the director of technology at the University of New Mexico Sovieta Field Station, where I've been working with sensor networks for over 17 years now.
Hey there, guys. My name is Connor Scully Allison. I'm the student fellow that's a member of the EnviroSensing cluster here. And I'm formerly with the University of Nevada, Reno, but I just graduated with my master's. I'm starting a PhD at the University of Arizona. And my master's studies was on quality assurance, quality control, and sort of the software systems to help make that happen specifically for streaming environmental science data.
Very good. We're going to go ahead and give you a quick overview of our cluster's activities. The plan for this session is to have a keynote from one of our guest speakers that came in this last year to our cluster telecons from the USGS, which is going to be a really exciting talk, and then have some talks by cluster members kind of getting into different technologies and techniques that they've been playing with in the last year. And we want to leave some room for discussion, for some group discussion towards the end of this session to talk about what you, really the embodiment of EnviroSensing and the EnviroSensing cluster, what you would like to see over this next 6 months to a year as we set our cluster telecon agendas and what topics we want to bring in. And we'll get into that a little bit later. But that's going to be the format such as this for this session. And so I'm going to give you a quick overview of what this cluster is all about for those of you who are not familiar. So again, we are a best practices community for in situ environmental sensing. So this is using kind of the IoT type devices to do work in environmental science. And the advance is not working.
Oh, click on the screen itself.
This one should activate. Yeah, there we go.
There you go.
All right, I just had to bring it into focus. Okay, so the whole reason why our cluster exists is because this idea of the Internet of Things has totally revolutionized how work is done across the fields of ecology, hydrology, biology, climate sciences, and it's really this phenomenon is driving kind of this mountain of data that we've heard about in some of the plenary keynotes that's overwhelming our traditional capacity to deal with these data. And so this cluster not only looks at the technology we use to acquire the information, but also what happens later on in the data lifecycle to deal with this deluge of information that's coming in, and how can we enable scientists who are not trained formally in our education. I certainly wasn't. to deal with this level of information in a way that will ultimately result in this concept of fair data and where we would like to go. And so we see that there are both benefits and risks to using the Internet of Things and applying the Internet of Things in the domain sciences. And so it's an inexpensive way to do your research. You can leave your sensors out all year, so it's unattended operation. There's a potential for better comparability because you have some idea of how the data were generated digitally. Multiple lines of evidence can help you answer science questions faster. Then there's these risks. So now you introduce multiple modes of error. You change the perception of whether or not the data are accurate. Oh, I have a number. It's not a NaN, it's a number, so it must be something I can analyze. And of course, we know that that may not be true. So these are some of the dangers that go along with it. And so we want to keep these risks and benefits in the forefront of the scientist's mind in these domains, and then move some of the practices and tool sets forward so that people can, again, generate some better and more fair data as they go on with their work. So these are our activities that we've been doing the last couple of years. We alternate between special projects and guest presenters in our monthly telecons. And we're always up for suggestions. We try to schedule the presenters 2 or 3 out. And but if you've got a special project that you want to bring into the community and discuss in a telecon, get some feedback on, feel free to give Renee and I an email, and we'll schedule that in, because that's what this cluster exists to do. Also, feel free to use the listserv. There are like close to 300 people on the listserv. Many of those are sensor and domain science experts that can help you if you have an issue. So feel free to make use of that listserv. So with that, I'm going to go ahead and get out of this presentation and bring up, maybe. Here we go. Oh, no, that's not what I wanted to do. There we are. All right. Wanted to bring up Joseph Bell from the USGS. So Joseph is going to give us his keynote on the USGS next generation water observing systems and designing that. We had Joseph's team in to do a guest presentation earlier this year in our telecons. It was really exciting. We're really looking forward to what Joseph has for us today. All right, it's all yours.
Thank you so much for the invitation to present today. And if there's any USGS folks out there on the line, thank you for the opportunity to speak for the survey here. I'm out of Baltimore, Maryland. I have a kind of a deep root in sensor workings with sensors. I'm a hydrologist right now, but I started in the survey as a hydrotech. And my first introduction to sensors or monitoring anything was in the military. And they put these sensors on helicopters to measure vibrations and frequencies. And if they were high, they were bad, right? So it kind of scared me the first time when somebody said, oh, the sensor's wrong, don't worry about it. I'm getting ready to fly in that thing, I'm going to worry about it. So, I had that root in quality control. What does the data mean? What does an outlier mean? And I've tried to infuse that into this upper level talk to give it the kind of roots to the ground at some points in time. So yeah, so thank you again. Really a fortunate opportunity to be here. If there's an acronym or something that you don't understand, please shout out so I can clarify that. So this is part of water mission area priorities, right? So next gen or water observation systems, next generation water observation systems, or NGWAS. These are all the kind of slang terminology for what I'm going to be talking about. And you can see it fits together in a chain, if you will. And this isn't just straight linear up or linear down, right? It's interwoven like a chain. And the next generation water observation system sits right here. This is what I'm going to be speaking about today. And with modernization, this is the web displays, and this is a huge part of this. Visualization, USGS really is putting a lot of work into visualization because folks need to see our data. And if you've ever gone to the web and tried to pull USGS data, you're in support of this endless modernization because it's not straightforward all the time, and it can be a bit tricky and difficult. Next gen deals with the sensors, right? Rugged deployments, prolonged deployments, Q&A, innovation, innovative approaches to both collecting and analyzing data. And then this really sets up the foundation for the modeling, right? The next generation movement really supports the modeling efforts, the National Water Model, and as well as the water resource, right? So water resources is huge. And I'm going to come up here and talk about the Delaware River Basin at the end and water resources. And it might be disorientating. It was disorientating to me on the East Coast, record rainfall past 2 years ever. And we're talking about lack of water possibly in the Delaware River. And I'll work through that scenario because I didn't really believe it at first, but the threat is real there. This is an iterative approach, right? So this whole project is going to move across the country, and so it's not just a one-time shot. So hopefully this won't be the first time that you hear about this, right? It comes from a challenge by the Academy of Science, right? And this is essentially a description of what next generation is, right? It's this enhance the temporal and spatial collection of data, the ruggedness of collection, and fit for purpose is really a big part of this. Not just collecting data for the purpose of collecting data, right? Just why is this data being collected? What questions is it trying to answer? And who do we have to get that data out to? So stakeholders are huge in this project, right? So local stakeholders, their wants, their needs, as well as and one of the stakeholders is Congress. So there's a big list of wants and needs from them. So we'll get a bit more into that. Right, 30 million stream reaches in the U.S. and the survey 0.03% of those have them monitored. So yeah, right, there's gaps in the data. They relate with communication gaps, right, coverage gaps, where there's no telemetry, where there's not good telemetry, there is a paucity of data observations, right? And this is just something I grabbed this morning to show current conditions, and there's no analysis in this. This is just observations. And part of the next gen effort is to not only provide the observations, but also to provide analyses as time series, right? So the continental shot there, you can see some of the higher elevations, higher elevated flows, right, associated with that tropical system came in. And then I pulled out Washington just to show how it's starting to get into that dry period, right? And I experienced the impacts of some of those fires 2 years ago when I was in Idaho, and the winds were favorable to the east, and there was really bad air conditions, and it really brings the whole thing together when you have these arid conditions and they spark forest fires. But the important part is to move towards monitoring in these gaps, right? And then I just want to point out one other thing. I took the kind of key topics of this session and the sense of data, technology, best practices, and I broke the talk up into a little of those sections. So this is something that's near and dear to me, right? SDI 12. When I got to the survey, it was like, we're still using SDI 12, right? Didn't we use this in the 80s? And then it took me a bit of time to learn about this, and it is a robust form of communication. However, I don't believe it's being used correctly, and a number of folks don't as well today, right? We can do a lot more with this, right? We can send commands, simple commands, but we only get one observation back. This is typical in the manufacturing world. You buy a sensor off the shelf, and you're going to get a single point observation. But how is it derived, right? One observation, is that good enough? And then any measure of variability, right? This is huge. Quantifying variability is a very important part right now, and it's going to be the future of time series collections. The keynotes, one of the questions from the keynote speaker really hit on that. And then the other side, RS-232-45. I kind of look at this as hijacking a sensor, if you will, right? Getting that industry motherboard out of the way and just dropping straight down to the sensor, right? Can I interrogate that sensor? Can I do what I want to do? For example, 1 hertz frequency. Can I force it to take a 20-minute or 20-second, 20-minute, 20-second, 20 millisecond unfiltered observation, and then I can do the algorithms and I can get the measures of variability, right? So this is a lot of stuff that NGWAS, the next gen effort, is looking at, and it's going to be important because we're also looking at bringing in LoRaWAN technologies and Internet of Things. So we want to have a quality assessment as well as a timestamp with this data. And here's a great example. The axes are removed. The plot is for instructional purposes only. A plot like this would never be on the web, because when USGS gets its hands on it, it would strip all this out in favor of that, right? Because that's noise. The important part is where that change occurs, right? So, to relate this back to the keynote speaker this morning, there's like the rock band, and then it goes into somebody who's really good at a violin. So it's like, oh, wow, racket, and then, this nice flowy movement. And, the noisy part in the beginning is that one observation, right? No variability associated with it. You don't know what it is. It's up, it's down. Could be real, maybe it's not real. There's this simple change to collect 20 observations in 20 seconds, average that data, and put it up there. Smooths the trace, right? You are starting to manipulate the data, so you have to worry about lags and components like that. However, from this approach, you also get those variabilities. So from one measurement, you're now starting to build several time series, right? You have the observation, you can also account for the variability, and you may be able to account for some lead lag time. Another part of NG-WATS, and this is a part that is a focus for me, right? This is where I came in. For folks that know the name, Brian Pellerin from the Hydrologic Networks branch, he reached out to me and brought me in on this. And the survey doesn't have a TRL, a technology readiness level evaluation, or a product maturity level evaluation plan. It really relies on the scientific method. And as we all know, the scientific method, you know, it's stout. However, subtle variabilities exist, and it's typically different from one scientist to the other. So there isn't a true standard way in the scientific method, if you will. The TRLs come from NOAA, NASA in the beginning, and then NOAA adopted off NASA. And then the survey is looking at these models, these TRLs, these product life cycle spectrums, and looking to adopt them. Right now, I have these little indicators on the bottom. The survey's in here, right? Some folks are early majority, most are late majority, and almost over here. There are few in the survey that are in the early adoption, and then even less that are in innovative approach. So the idea is, if we can shift this just a little bit, right? Start to pick up more early adoption, early majority, we can get more out of the instrumentation and for a longer period of time. The idea behind this also is to improve communications with the manufacturers. It doesn't do anybody any good, especially the survey, to say to a manufacturer that they just bought 100 or 1,000 data loggers from, or 1,000 sensors, and say, hey, we really need this function. And the manufacturers come back and say, well, you should talk to us about 6 years ago, because we're not even updating this anymore, right? So that's really important. Promote innovation, right? Everybody knows that these are valleys of death in here, right? You have an idea, how do you go from observation, or from innovation to observation? Well, you have to cross these valleys of death to get the project going. Maybe it's a great idea, but you just don't have the funding. A lot of times in the survey, we have great ideas and they get far, but we don't have the production power. So when we get to these TRL 6, 7s, and 8s, we can get a prototype out there and we can test it, and the prototype can pass and do well. However, we don't have the resources to manufacture these like the manufacturers do. We don't have 200 engineers working every day on a specific topic. So we're looking to improve the communication, promote innovation, and be more reactive instead, or I'm sorry, be more progressive instead of reactive. Not having the manufacturers in the market drive us. Maybe we can drive the market a little bit. A really good example of this is in the hydroacoustic world. When hydroacoustics first came out, they had that measure of backscatter, right? It's a signal to noise ratio measurement, and it's a measure of quality. Well, somebody really smart figured out, hey, we can use backscatter as a proxy for suspended sediment concentrations, right? They're particles, they reflect sound, and energy, and we can set up a relation with them. Well, folks from the USGS went to the manufacturers and said, hey, can you take this data that is ancillary and buried deep and bring it into the forefront and allow us to be able to get it from an SDI 12 call? And it was reluctance there, but it really is a good example and a good stepping stone of, if the USGS and the community was a bit more in their early adoption, there was a lot more opportunity to work with the manufacturers. So, and then a positive market disruption, right? We don't want our data loggers to be held hostage by any one manufacturer, and also we don't want a manufacturer to just keep climbing the cost ladder, right? It's like, oh, you paid for 5,000 last year, maybe you'll pay 5.5 this year, and so that's the component of adopting the technology readiness plan. A key part of it is also passing on the information. I know I have gotten a sensor from a manufacturer, worked on it, found the pitfalls or the good, used both, and then just kind of moved on and didn't pass that to any of my colleagues. And that's a flaw, right? That's a fail. So somebody else in New York, if they're going to pick up that instrument, they really have to start over. So this idea of organizing these plans and testing these instrumentations is really important, right? And then technology. So we talked about the in situ stuff and better SDI 12. One of the other things we're looking at though is non-contact monitoring. And this plays into cost of ownership, right? Every time you send somebody out in the field, it costs money. And a lot of you folks work in really rugged conditions, so you understand the resources it takes, right? Sometimes you have one shot to get out there, a year to get to this stuff. And if it fails 2 weeks later, that's a big fail. So this idea of non-contact monitoring to lower the cost of ownership, lessen the impacts of biological fouling and even calibration drifts, and also innovation, right? Get to a place that you can hardly ever get to, really remote, and be able to collect observations. I'm showing a picture from Virginia here, so it's easily accessible. But this could be anywhere though, and we can shrink this down and call it a mountain stream, right? The headwater stream, where it's more debris flow-esque than it is really waters. And this idea of image velocimetry, the software and the algorithm and the procedure picks up on particle movement. It is on the surface, so right, we have to account for that, or at least just disclaim it away. But it picks up on the particles, and we can use that velocity from the particles to render a discharge estimate, right? And this is huge because, like I said, this could be done in remote locations with cameras where they can be set up to event trigger, right? So you may have one sensor that says, we just got 5 inches of rain and you're in the watershed, you're 3 miles away, you are now going to get inundated. Start your video, right? So boom, the video collects, and now you can start to capture these observations that are in locations that are really remote and rugged. So Frank Engel, Jack Eggleston, John Fulton from the USGS, really brilliant minds, others as well. I'm not capturing them all. They're working on this, and it's really close to getting this out of a TRL state and into production, right? There's a number of hurdles left, right? We have the policy component we have to take care of. So, and then as well as building these things out, right? So this is an opportunity for the survey to reach out and say, we have this kit, right? What manufacturer wants to get in with us and expand the capabilities and get this stuff out? Another component of non-contact monitoring, this is from Paul Kinzel, Jack Eggleston as well. It's important to point out here what you're looking at, the structure on the right isn't ice. It is thermal differences across the cross section. I have a video at the end. I don't know if it'll play. I didn't take the risk to go live fire here, so if we have a bit of time, I'll play it. But this is differences in the thermal properties of the cross section. And when you look at it in this view, you can basically see these warmer or cooler sections, if you will, moving through the imagery, and you can use those to derive a discharge or a flow velocity. In this particular instance, they were using airborne aircraft, so a drone, and then they were using a platform, stable platform, to correct or provide control for that. So really, really neat stuff. You can take this one step forward and start to look at other applications, right? So it's not just water that we're looking at, other media, right? This doesn't have to be on Earth. This could be on, Mars, or getting wind speeds and alien processes. But this is Kilauea, right? So this is a group from the USGS, thanks to Jeff Sloan, Joe Adams, he's at this conference, really great people. And right, so I have to disclaim it away, not for citation, not for distribution. I don't think this has hit a publication yet. If it hasn't, it's in works. You'll see it soon. But if you Google USGS Kilauea, Hawaii, you'll see some pretty awesome footage on the web. But this is another practical application, right? How fast does velocity flow? How would you ever measure that before? And here's a pretty good way of getting at a rough estimate, right? You still have to do something with the cross section, and I'll let Jeff figure that one out, because you need the area component, right? And then probably the last one I think I have for the last one I have for non-contact monitoring, again, right? Point source input. We can find groundwater seeps coming in. We can also find maybe illicit discharges coming in. And then we can use it on the QA side for cross-sectional mixing. You go to the USGS website and you pull up temperature, and you're gonna find a slew of real-time temperature observations. But are they representative of the cross-section, right? That's a good question, because these units are typically on left bank or right bank, and they're projected out across. Now, the survey does painstaking efforts to get that representation by sampling across the section. However, this is easy, right? You show up, you pop up with your drone, you take a thermal image, and you're done. Boom, you're gone, next site. And then as well as the algal bloom tracking, right? This is Lake Okeechobee. You know, we can use these non-contact airborne techniques to track it, but then possibly even forecast it, right? So really cool stuff there. I'm going to follow a bit on the QA. The next slide is going to be busy. I'm going to walk you through it. It's one of the ones that I would typically click through, but I didn't want to take that risk either. So you know, following up on the QA and really addressing an answer of a question. I'm going to get into the Delaware River part where we're focusing on temperature and conductivity a lot. One asks, well, is temperature next generation? Is measure, is an observation of conductivity next generation? Well, no, we've been doing that for years, and so has a lot of other folks. However, what we do with that is really important, and the next gen component to that is this idea of real-time data QA/QC. And you know, how can we get either microprocessors or data loggers themselves to start to generate corrections on the fly, right? So here's a great example. Don't worry about the numbers. I know it's small font, but really what we're after are patterns in this. So we have turbidity in orange, discharge in blue, and coefficient of variation in this purple magenta. And what we can see is a storm comes in, really nice, little bit of scatter, but then the flow kicks in, really good, really good quality data, low variability, goes up, starts to peak, comes down. This is a gain issue with the turbidity probe, so just keep that in mind. And then as it comes down, right, you start to see a lot more variability start to get introduced in the system. And this is typical, right? It's an optical instrument, sediment deposits, it gets on the optics, it messes up, causes fouling. In the past, it would have typically been cut it in half, start the correction back here. Now we're looking at the aspect of measuring the slope and then maybe going back and correcting on the fly. And we're also looking at single point exclusion, right? What's the variability? Is that a spike or is it an outlier or is it trash? Well, in this case, you get this huge spike, associated huge variabilities, boom, it's gone, right? So you're starting to look at this QA/QC process. You always maintain the integrity of the original data. That is not going to be lost. However, you don't always, we look at this relation, right? The telemetry requirements versus processing. We can come and download this at a later point in time. If our budget for telemetry is low, then we want high on-site processing, right? So it kind of makes sense. So we're struggling. USGS is not struggling, but working through where do we want to put this. And the question and the answer to that, I think, is situational, right? It's going to depend on what it is you're monitoring. One last part about the best practices is spatial extent. This is the buzzword structure for motion, advanced photogrammetry. This is really neat, but it's ground-based. So this is a fantastic experience that I've had, and I think anybody who's done sediment monitoring has had it as well. You show up, you put your bank pins in. Bank pins are just steel rods. You slam them in the bank, and then you say, this is time zero, so we're going to measure it from here out. But then you go back and you see this massive slump, right? What happened? How do you account for that? You can't really. So you blow out your spatial extent, and if you get your wellies on or your waders, you get in the stream. This is a stream bank, so if we're looking at this, the stream comes this way. There's another bank here. We took a series of photographs through time, and then we can do difference mapping and render the erosion spatially. And I know it's not up here, but to tell you, these are on the order of centimeters, these are on the order of meters, right? So the true erosion rates. I'm going to move a little faster. I don't know if this video is going to work, but this is a place where I would really like to learn, because I want to sync this video to this time series, right? So this is another part of NGWAS, is introducing cameras, and cameras in more than just looking at a point or a stage plate, right? Simple, small flow. So much going on here. If you're a freeze thaw addict, if you're a geomorph dude, lady, person, lots of fun in this video here, and then the associated time series, right? So you can see stream comes up, stream comes down, and the turbidity follows suit. This is that slump that I showed you before, and how the water has eroded it away. So basically you see this loading and unloading, and this isn't even a high flow. So what happens in those high flows? So what I would love to do is kind of image an image and match that up. So hopefully one of my next presentations to the group could be that, right? I'm going to jump into the Delaware River project really quick. Delaware River was chosen as a pilot for the NGWAS study. It's politically charged water basin. It's also it is the only river in in the survey's scope of work that has a court order, right, and a regulatory component. There's a dissent decree that says flow must reach a certain value at the Philly intakes, or and if it doesn't, then the reservoirs in New York must release. And reservoirs in New York, they do their calculations and they say, well, you should have this much. And if the river master is asking for more, they say, can you justify that? So we're looking at improving those models and data densification as well as diversification. So in 2018, we looked at the map. The group looked at the map: New York, Pennsylvania, New Jersey, Maryland, and Delaware for spatial reference. And then the blue dots were existing, the red dots were added, and it just made sense. And we're making a first cut at this, so we didn't have an ability to really do a lot of sensitivity analysis, and that's where the modeling component is going to come in that chain, because it's going to feed back in and say, hey, you didn't need all these, so you can pull some of these out and just keep those sensitive sites. In 2019, we expanded a bit more out into the fringes. The green aren't all new. The red gauges were new. The green are just enhanced. So it might be somewhere where we put turbidity, might be somewhere where we put a nitrate sensor, conductivity. And now I'm going to go into that kind of the stress on the system. Right, you have saltwater wedge coming in from here, Philly intakes about there, and then you have the never sink reservoirs up here, which are either flooding it or restricting the flow, right? So you kind of have this dual pressure on the system. And one of the things that we're looking at to integrate into this project is the LoRaWAN technologies, right? And I'm super excited about this. 4 months ago, I didn't even know what this was, right? David Coyle got in with the ESIP group and presented and said, hey, you gotta get with these folks. They're really hot on this stuff. And from there, it's been a fantastic experience, a great learning experience. So one of the things we're looking at is with the Carnegie Mellon Institute, Bob Iannucci, John Stock, Matt Morano from USGS are working with Bob, and we purchased a couple of sensors and some gateways. And what we're actually looking at doing is we're going to put a LoRaWAN network up top and a LoRaWAN network at the bottom, so that we can look at some of these reactive sampling approaches. And we can also start to explore surface water, groundwater interactions, right? We can have soil moisture probes along that cross section. We're looking at the possibility of making a USGS gauge station into a gateway node. And we're going about this without the manufacturer's kind of homegrown network, so that we can invite other folks into our network. We can be in control of who is in our network and who is using our network. And it'll be a public network in a sense, but we're gonna say, hey, if you want to play, these are the restrictions and whatnot. And all of this is going to change. It's an iterative process, like I mentioned. And one of the things that we can see as we march across the country, integrating watershed monitoring is this development of a countrywide long-range, low-power network, right? And the ability to connect with other groups who have existing networks. So the flexibility is key. Right. So proposed for 2019, non-contact velocity, right? We covered that a lot. Video imagery and velocimetry, huge component of it, right? How better to use cameras when you can see it happening, it's so much better. This is going to improve quality, because some folks work stream gauge records that have ice impacts that don't have video or don't have an image. Well, how do you know ice was there? Well, experience. Okay. But if you had a camera, you could just bring that up. So there's a lot of benefits, cost of ownership to coming down. eDNA is on the focus for 2020 as we look at the next basin, and maybe even in the Delaware itself, and some of the other things as well, like suspended sediment sensors, particle size sensors, to bring it back and close it up, right? It's an iterative process. We're starting on the East Coast. It was the basin was basically chosen for us. The next basin will be out west, and you can kind of take a shot at which one that's going to be, right? So politically impacted water resources, somewhere in the Rockies. Super excited about that. Really fortunate to be part of this group and part of the survey working on this. Thank you once again. These are some contacts if you want some more information. Chad Wagner, he's the program coordinator. Mike Woodside for the USGS folks, he was a big NACWA guy. Fantastic leadership. And Brian Pellerin on the bottom, I put him in. Brian is a mentor of mine, and he has really I think he's done a fantastic job with me as a professional, and I really appreciate his leadership, and he is working on this project as well. I think that's it. So that's the thermal trace. Next time I'll have a little more confidence.
Cool. So we have time for a quick question while we change speakers.
This is something just going to be a naive. It's the LoRaWAN.
Yep.
I
Sorry.
will answer to my extent, and then others can come in. So the LoRaWAN is long range, low power. So what you're looking at doing is you're not being restricted by the typical sensor power budget, right? You're going down to that probe that's on the sensor, and you're getting an observation, and you're using radio comms to tie it back. And for folks that's used radio comms in the past, it's line of sight typically, right? So you don't get good ranges in dirty environments, dirty with respect to radio waves. The LoRaWAN is boasting kilometers of distance and 2-wall penetration. So we're gonna see. Did I butcher that?
No.
Great.
We're good. All right. Well, let's give our keynote a hand. Thank you, Joe. Excellent. Okay, our next speaker. This is on. It's not on. Okay, our next speaker is going to be Martha Apple from Montana Tech, and she's going to tag team a presentation where we're going to hear a little bit more about LoRaWAN actually from James Gallagher, who will be right after. So let me know if you need me to change the presentation in between, but otherwise,
Okay,
if you want to really walk around, you can use this. Otherwise, it sounds
I'll
like I'm
just
picking it up.
probably be stationary, semi-stationary here.
Okay.
Hi, everybody. I'm Martha Apple, and thanks for the introduction, Scotty. It's good to be here, and I want to tell you about the ecology, botany, microbiology, outdoorsy part of fitting a field experiment and expanding it into one that involves sensors. So this is a picture of Saye Pass in Glacier National Park, Montana. And here we have patterned ground. You can see some striped areas on the hillside. Do I have a pointer here, or should I just use one? Okay. So here, right there, this pattern, I'll just use the cursor, pattern ground is striped, and this comes from particle sorting and freeze thaw near glaciers. And so we have been studying plants and microbes of that area. And with the idea of expanding this into looking at environmental factors that influence the plants and microbes, such as temperature and soil moisture. So this first part is microhabitats and plant functional traits, and that's me, and I'm from Montana Tech in Butte, Montana. And then we'll have part 2, which will be by James Gallagher, and you'll hear more about LoRa. Okay, so these snowy alpine environments are complex and have microhabitats and environmental gradients. And the reason we're studying this in the first place is because the snow fields and glaciers in the Rocky Mountains and many other places are diminishing and in many cases disappearing due to precipitation changes, climate, which are driven by climate change, increased melting, and so on. So we want to see what's out there and how the plants and microbes and ecosystem in general respond. But we have lots and lots of variables, slope and aspect, patterned ground, gradients of distance from snow, the snow itself, what are the substrata, the snowfield edge. The snowfield edge community is a dynamic place, and the snowfield edge melts off seasonally, and you get a little community right along the edge. Okay, so what are plant functional traits? I don't think everyone here is a botanist. So they are characteristics of plants that interact with the environment and govern where the plants can live in response to environmental factors. So examples of these are height. As you might imagine, many of these plants of the alpine tundra are not very tall. This is Aquilegia jonesii, the Jones's columbine. It grows on calcium-rich or limestone substrata. It has divided leaves, which help dissipate the incoming solar energy. It has a cushion morphology, which decouples its heat signature from its environment, so it doesn't freeze or heat up overly. The complex flowers are able to attract pollinators, which are somewhat few and far between in these high mountain environments. And it has a taproot for storage, and this plant can actually move downhill with a talus slope. And it's symbiotic with mycorrhizal fungi, which supply nutrients for it. So we have a paper on this in which we looked at plant functional traits and microbes and found that they vary with position on paraglacial pattern ground. And that's at Glacier National Park in Montana. So more recently, we've set up another experiment at Goat Flat, which is in the Anaconda Pintler Wilderness in southwestern Montana. And there, it's a little easier to get permits for research, and there's also paraglacial pattern ground. So pictured here, we have James Gallagher, and who's going to be speaking to you next. Kevin Nagus, who's in our group. He's an electrical engineer who's interested in sensors and ecological problems. We also have Xiaobing Zhu from geophysics, who's interested in bringing a drone up there. And at the last talk mentioned heat signatures, which I think would be really interesting to get from there. And we have the intrepid Curtis Winscott, who helped me install sensors and label the sites. So last summer we established an array of sensors, and these are the little hobo tidbit sensors in microhabitats in the soil, and we have placed some of them in the center of these polygons of pattern ground where ostensibly it's hotter and drier. We're hypothesizing that. And then along the edges, we have other sensors, and that's where there's probably greater moisture and probably more even temperatures, but we don't know that yet. And what we're going to do is go back pretty soon after a big snowfield that blocks the trail most of the year has melted off, and dig up these sensors, extract the data, and then haul it back home on our laptop. So it's a little cumbersome, but hopefully it will work. Hopefully we will be able to find the sensors, because as you can see, this is a somewhat homogeneous environment. It's several kilometers across, and where did we put our sensors? And it's also right along the Continental Divide Trail, and it's a mecca for wildflower enthusiasts. So you don't want to put anything there that's too obtrusive. It's also the alpine tundra. It gets a lot of snow, a lot of wind, and leaving things that are going to be blown down by the wind or examined by hikers and other curious animals will, not be very conducive to getting the data and finding the sensors. So we installed these, and this is the kind of signature you get. This is over several years. This is from a different study, and this is at the top of a nearby mountain. So things we'd like to find out from this are just considerations, requirements, and possibilities. Goat Flat is accessible only in late summer after the trail clears of a steeply angled snowfield that's across a cirque. You really do not want to slip and fall there. And as of now, we know when it's open by word of mouth, essentially. Hey, have you heard if Goat Flat is open yet? Nah, another week or so. And which is hard for planning research trips. And we'd like to be able to detect when the snowfield is melted. We'd like to improve methods of finding sensors, and the sites are now marked by red paint on the bottoms of the rocks, and photographs and GPS coordinates. But essentially it'll be like, oh yeah, I recognize that, and pattern recognition. And we'd like to possibly use RFID. We need to avoid leaving objects above ground because of the wild animals, et cetera, et cetera. So we need inobtrusive sensors. We'd like to remotely access data from sensors under snow in a cold environment. And by cold, I mean it gets down to approximately minus 30 degrees C for air temperature in winter, and possibly do this with LoRa. And this would be very nice. You wouldn't have to wait until you could go up there to get your data. And you could also know if a sensor has failed. An online access to data in near real time, as I said, could get data more frequently than once a year and could check for sensor failure, and then develop soil moisture sensors that can realistically be left out in the alpine tundra all year. And soil moisture is very important for plant and microbial life. And these sensors would be low cost and low power, so you could set up enough samples to be ecologically relevant. So those are some things we'd like to see. This is September at Goat Flat. And here you can see the pattern ground, and we have the clearings are the centers of the polygons where we think it's likely to have lower soil moisture and more extreme temperatures. And then the edges are where we have evergreen dwarf shrubs and more snow accumulation, at least early on before the deep snowpack forms. So that's essentially what I had to say. And thanks for coming to this talk and listening. And here we are. Okay.
Thanks, Martha. It's a classic problem for many people in our field.
Right.
And I think you've set it up very well to talk about how you try to solve some of those problems.
Right, right.
So we're going to hold questions, I think,
Got it.
until after James has given his, if that's okay.
Here comes James Gallagher.
So I gave you the wrong talk.
Oh.
So can I give you a different talk?
Oh, sure.
You want to do a different talk?
Yeah.
Maybe we've got time for, if anyone has a question for Martha while we're changing talks.
Can I just crank it up?
Go ahead.
Okay, it's the type of thing, you know, I'll just talk at you for a minute while he's setting that up. It's actually a chance for community growth.
Do I just make it big?
I think so.
And I explained that we're looking at effects of climate change on plants. Oh, I'm interested in that. And it's really a nice sort of information.
This GoToMeeting's being a jerk today. It should probably be good.
Yeah, we're good.
Okay, cool.
It looks like, okay, so community outreach is what you were talking about.
Yeah.
And yeah, I would imagine. So James works very closely with Martha. I've actually known both of these wonderful people for a long time in the mountain climbing community. I'm really glad to see you here at ESIP. And so I'm curious to see what you've come up with in solutions.
Okay, well, I should say that we are married. So we're going to talk about, so Martha set the stage and she talked about requirements. And so I'm going to first of all take a look at the basic design that we have come up with based on those requirements. Now, I should also say that I've been going in the field for decades. So I'm kind of familiar with a lot of the stuff she talked about, at least at the, put the backpack on level. Initial design criteria, we're going to deploy sensors initially at one particular research site, and that's Goat Flat. And that's about 9,000 feet elevation. The sensor nodes need to be low power. They need to operate on batteries autonomously for at least 2 years. 2 years is important because sometimes you can't get up there before the snowpack gets back in place. I mean, you're juggling all the usual logistics plus the rest of your life, right? We want to use LoRa because we want to be able to connect these sensor nodes, a fairly large number of sensor nodes that will be low cost, to a relatively small number of master nodes. And then we want to have the master node forward the data to the internet. The master node can use, well, in our initial design, we're going to use cell phone technology to get data out of the master node and onto the internet. And we know that we can do this because we know cell phones work up there because Martha's had students talking on the cell phone when they should have been working. But that's not the only way, okay? The SNOTEL network uses meteor band radio, so lots of other technologies are available for these rugged environments. But we know cells will work. We know cell towers are going to work at Goat Flat. We know they'll work at a bunch of other places. Data from the master node is going to be sent to an application server that can be accessed by browsers and analysis tools. And we will attempt to mark our sensors so that they're recoverable using RFID tags. Kevin, who Martha showed in one of the slides, he's done a lot of work with RFID tagging and finding things and using relatively high power RFID sensors. The master node can be not quite so low power constricted. It can have solar cells because there doesn't need to be a lot of them. And I'm going to spend a fair bit of time talking about LoRa as I go on, but the master node has a bit more flexibility, and it can do things like tell us about other parameters like snowpack and stuff like that. And then finally, we have to think about calibration. So right now we're planning on using a fixed base like lab soil moisture sensors and temperature sensors to calibrate these beasts. So I'm going to kind of mix this with our design and also a bit about LoRa. So typical LoRa deployments use something called star topology with a master node at the center and sensor nodes out at the edges. The sensor nodes collect data and they fire that data into the master node. The master node pumps that data up to the internet. And so here is a typical sort of like scenario that you go through. Essentially, the sensor network is asleep. Then the sensor network wakes up and those sensors begin to measure parameters. The sensors send data to the master node and then the sensors go back to sleep. Those sensors are on for maybe a second, okay? And they're sampling maybe once an hour. The master node processes the data and fires it up to the internet, up to an application server, like a cord server. And then the whole thing goes back to sleep again. It's very low power. So there are a couple of things about LoRa that you want to know. And the first is that nominally it's a point-to-point radio technology. However, because it's a radio technology and because it's a networking technology, there's protocols involved, right? And so there's a couple of general types of protocols we could talk about. One that's already been mentioned in Joe's talk was LoRaWAN. That stands for Low Power Radio Wide Area Network. And one of the advantages of that is that it's low power. It's a wide area network, which means that it supports reliable transmission. Nodes are not actually responsible for error correction. The protocol handles error correction and retransmission. And also LoRaWAN handles security using the AES security infrastructure. Another type of protocol is an ad hoc protocol. That basically means you roll it yourself. You can leverage things about the specific problem to design the protocol to drop the power requirements even lower. However, it's a lot less flexible than LoRaWAN. And it means you're writing a lot more code. You're responsible for error correction. You're responsible for security, all that stuff. You got to do that. And there's things in between. There's a mesh network technology that I'm not going to go into now. That's a kind of an in-between thing. So what have we done so far? We've built 3 prototypes and tested them in various environments. And this is prototype number 3. The information on this slide is an amalgam of those 3 prototypes and what we've learned from them. This prototype has a LoRa married to an Arduino, which is a 32K flash MCU type unit. And it can sense temperature and soil moisture. The sensor's up on the top there. It's powered by a couple of lithium manganese oxide batteries that are nominally rated down to minus 50 degrees C. And it has been operated down to about minus 25 or minus 26 in our backyard. We've tested it buried in snow, we've tested it buried in soil, we've tested it inside concrete blocks, and we've tested it in an open air. The total parts cost for this unit here is about $40, but we can almost certainly cut that in half, including the cost of the case. The master node for these tests has been a Dragino, which again marries a LoRa with an Arduino and a Yuan single board Linux box. We're sending the data up through the internet to a Cord server. The protocol that we're using, again, it's star topology. It's an ad hoc protocol that I wrote myself. It's based on the notion of a reliable datagram. I'll get into that in a little bit in a moment. And again, the application server is the Cord server. You can look at it using that URL on the bottom, which I don't expect you all to read, but these slides will be somewhere. Please don't download all the data because OpenDAP is provisioning that server. But anyways, this is some sample data. This is from the 3rd to the 28th of February. We were testing battery drainage. So we ran the thing. We intend to run this sample at about one sample an hour. But here I'm doing, I think, 1 sample a minute. So we just ran it out as fast as we could. And you can see the temperature data coming back. And we have soil moisture data and a few other things. LoRa produces a lot of really interesting information, including signal to noise and received signal strength. And that allows for even simple protocols, even a datagram protocol, to be adaptive in terms of transmit power, which is a really key thing. So a lot of people have been asking questions about LoRa. It's kind of cool. LoRa, short for long range, it's a spread spectrum technology. Spread spectrum means that you take a relatively narrow band and you plaster it on top of a much wider radio band. In particular, this uses chirping and frequency hopping. And I can't quite explain all of those things right now. Chirping is used in radar, and frequency hopping, interestingly enough, was invented by the 1950s film actress Hedy Lamarr and her partner George Antheil, who is an avant-garde music composer. And they developed it. You can read all about why they developed it under certain circumstances. It's an interesting story. Some LoRa specifics, if you're really interested in this stuff. These units are very small. You can see up there next to a quarter. They're inexpensive. You can get them for $5 a unit. They have a good range between 1 and 10 kilometer. They have relatively good bit rates up to 37.5 kilobits per second. They work well with LoRa or Arduino and other microcontroller units using like the SPI interface. They have good frequency bands. They work well in Europe and Australia and the US. Relatively low power, 20 milliamps to receive, 100 milliamp on the transmit burst. LoRa WAN and where it fits. I put this slide here because a lot of people might not be familiar with how layered networking is handled. But the lower level is the actual physical layer implemented by the radio hardware. Okay, and this is responsible for encoding the information for the chirping, the spreading, and the frequency hopping. The layer up above is the wide area network, and that incorporates things like the security and whatnot. Again, we're using point-to-point, so we're not actually using LoRa WAN, but when you are, this is the kind of technology you're using. Some really interesting things that I kind of skipped over. There are a couple libraries that are available as open source. One is called Radiohead. That's what we're using to do the datagram. Tiny LoRa, which is published by Lemore Freed, who's the CEO of Adafruit, is an implementation, a free implementation of LoRa WAN. And then the last slide in my presentation where I say thank you for putting up with all this stuff is way too small to read, but it's got like a bunch of clicky URLs that I thought were really cool while we were going through this design process and breadboarding these things and stuff like that. So with that, thank you. I'll take any questions.
Questions for James on LoRa? And
Yes.
getting to do
Just a
super.
point of clarification on the range, you had 1 to 10 kilometers, and that is from the smaller sensor to the hub, correct?
Yeah, that's correct.
So the hub can be, and then from the hub you have a range of
whatever you can get, whatever technology you can deploy. Like for example, we're planning on using 2G cell. And so 2G cell goes up and then it's on the internet. The idea, I mean, a basic requirement that Martha articulated was that we need these data to be available near real time, right? Because this is a hard place to get to. And when sensors fail, we want to know about it as soon as they're deployed so we can like go back while it's not snowy. But also it would be really cool to be seeing the data as they evolve over time, because then you might be thinking, well, now I know this, I can use these 6 months that are snowy to plan the experiment and, you know, the next iteration of the experiment. Because like she's working with undergraduate students, bringing them up there, you know, it's like a huge logistical thing. These things are huge logistical problems.
One more.
A quick question on if using a star topology, that I assume that means you cannot do multi-hop. Is that correct?
So you can. So you can deploy mesh networks with these as well. The radio units are transceivers, but mesh networks consume more power, right? Because a receiver has to be on to receive. So you got to wake all the units up in unison, or a more complicated scheme.
A follow-up, sorry
yeah,
for that, is with the star topology, are you synchronizing the base station wake up?
Yeah.
Okay, thank you.
I'd like to talk about that all day. So maybe we can meet later and we can all have some more LoRa discussions. I foresee more LoRa discussions in our monthly telecons in the near future. So next we're going to hear from Renee on her adventure this last year in McMurdo Dry Valleys. And Renee, take it away.
Thank you. Today, I'm excited to talk to you about the McMurdo Dry Valleys LTER, Long-Term Ecological Research Site, where I've worked for the past 2 years as a data manager. I have been working with sensor networks for a long time, but taking this position, I was sort of a promotion for me. And you know, my experience working with sensor networks has given me a really good understanding of how to manage sensor network data. And as we all know, there's a lot of challenges with that. And in this talk, I'm not really going to talk a lot about the details of our sensor networks. It's not really what I do there. We all know what a lot of these pros and cons are, but rather I'm going to talk to you about the unique constraints that this environment has and some of the more about the human component of that. So as a data manager, I think it's extremely important to go in the field, to have work with the researchers to understand the types of data that are being collected. I had the opportunity to deploy to Antarctica this past season for 2 months, where I worked on the ground alongside the researchers, and so I'll be talking about that today. Just a little bit about the LTER, for those of you who don't know. I know there's a lot of us in the room. So it was established in 1980 by the National Science Foundation for a couple of different goals that are listed here. I have been working with 2 LTER sites, Sabieta in New Mexico, where I'm based, and the McMurdo Dry Valleys in Antarctica. There are 28 sites. Currently, that number has fluctuated a little bit over the years. There are 6-year funding cycles that can be renewed, and each funding cycle usually focuses on a different theme. So a little bit about my background before I jump into McMurdo. I was hired at Sabieta to be the system administrator. Because I knew something about technology, I was quickly recruited to do things in the field, like set up large-scale wireless networks like this one that we established in 2004. Which serves a very large area in central and northern New Mexico and streams data from lots of different kinds of sites, including eddy covariance flux towers. So we use a standard off-the-shelf Wi-Fi for this network. I also do these very large-scale climate change experiments, heavily instrumented. This is one of them. These experiments are largely focused around issues that we have in the southwestern United States: drought, changes in rainfall variability, and so on. My latest project at Sabieta is the upgrade of a large-scale weather station network. I received some funding from the NSF Field Station Infrastructure Program to just bring this technology up to the today, basically. So I'm excited to be working about that. And then one of the other things that I do is teach a short course on environmental data acquisition at the Sevilla Field Station. We've been doing this several years now. The next one's going to be in June 2020. This year, I'm helping Mark Gaylor, who's in the audience, at North Temperate Lakes with aquatic-based sensors course that's going to be using Arduino. Our course is focused more on terrestrial networks using Campbell Scientific equipment. Getting into the McMurdo Dry Valley, so this is what it looks like. It's dry, very dry, but there is a lot of water, but it's all tied up in the glaciers. So we can see the glaciers falling down into this valley. The glaciers melt in the summertime, which is not very long, and form these ephemeral streams that you can see at the valley floor, and then those streams flow into closed basin lakes that are ice covered year round. Next slide. Oh. Okay. So, whoa, okay. There's my whole talk. So this is a map showing the setting of the dry valley. So it's obviously located in Antarctica, shown in the top left. And these are the different, there's several dry valleys in this area. And I don't actually know why it's called McMurdo Dry Valleys, but my guess is that they're named after the nearby station. So there's a US supported station about 45 minutes by helicopter away from there, and that's how we get there. And so what this figure is showing is all the different types of data that we collect in this system. So we have lake monitoring, weather stations, stream monitoring, and soils. There's also glacier monitoring as well. And our current research focus is on connectivity. So all of our hypotheses and research questions are around this idea of connectivity. So we have hydrologic connectivity being the big one, but also focusing on other forms of connectivity. Before I can talk more about the data, though, one of the things about working in Antarctica is it's very difficult. It's not easy to get there, and the living situation is primitive at best. So on the left is my tent. That's where I was living for 2 months in the dry valleys. It's gorgeous, it's amazing, it's surreal. The top right is the McMurdo station. This is where we fly into, but as field researchers, we don't spend much time there. And then the lower right is a picture of the inside of the building at my camp. So we sleep in tents, and then we have these buildings where we can cook our food and do lab work. And I was at the smallest of the Dry Valley camps. It was quite it was an interesting experience, to say the least. So yes, so to get there, it takes a really long time. It's several days from leaving the U.S. to actually getting to Antarctica. You fly to Christchurch, New Zealand. You spend a couple days there. You get some clothing. You get some training. You have an 8-hour flight on a very uncomfortable military plane to McMurdo Station. And I don't mean to sound negative about this experience, but I'm just providing some reality here. So when you're in the field, it's daylight 24/7, which is not bad, actually. We live in tents. We don't have access to showers. We don't have access to laundry. All of our waste has to be removed. If you have experience working in the field, we have such a thing called a pee bottle that is an Nalgene bottle. So they're really concerned about preserving this delicate landscape. Our camp is powered by solar power and propane. We actually eat pretty well. We drink water from the lake. There's not a lot of life here, so no animals, no higher plants, just a lot of microbes and algae. I'll talk about that next. Getting around, so I already talked about how we get there. Getting around when we're in the field is largely by helicopter and by hiking a lot. And so in the top left, I show a picture of the helicopter, and it's carrying something, and that thing that it's carrying is an ATV. And we use ATVs on the frozen lakes before the edge of the lake melts out. We call it the moat. And so those are kind of an early season thing. Our ATV got stuck and pretty much ruined on the lake, so they brought us out a new one. And so helicopters not only transport us, but they transport all of our equipment as well. And so just an overview of the data. We have over 25 years of ecological, physical, and chemical data sets. Our data are generated in two ways. The most common way is through field collected samples by humans, but we also have some high frequency continuous data sets, such as environmental sensor networks. Also satellite imagery is pretty common. Drones haven't really started taking off down there, but I expect that to be in the near future. Our field season is only about 3 to 4 months long. Most groups deploy for much shorter than that. Field work occurs pretty much every day of the week, regardless of weather conditions. So that can be interesting, to say the least. When I say that deployments depend on timing, that's because the sun starts to come up around August, and the glaciers don't start melting until and forming streams until November-ish. And so the real core work in the streams doesn't happen until later in the season, and same with the soils. The soils are frozen. So those soils folks typically work in January. Our standards and access policies are set by the NSF and the LTER. Our data are organized by core area, and so these are some of our core areas. We have glaciers. This is the part where I show you lots of pretty pictures of Antarctica. And streams, of course, and so these can be anything like a fairly large stream on the lower right there with a weir, to these sort of ephemeral streams that fan out. When I was down, I was deployed with a team called Algalops, which was a fun team. It was me and Josh, who's shown in the picture here, and we were collecting algae, which look like this. They're pretty impressive. A lot of orange and black and a little bit of green algae, as well as mosses. And so we have these long-term transects along all of the streams in the dry valleys that we collect algae from. And so from all of these different core areas, we collect biotic data, chemical composition, and in the glaciers in particular, also mass balance. And then, of course, we have soils. We have a lot of it, and I really regret not showing a picture of our polygons that Martha showed. We have some quite impressive polygons, and it'll be interesting to see how climate change affects those in the future. And then, of course, we have weather stations. And so these data are also telemetered. So we have 14 weather stations across the dry valleys. The data are streaming year round, and including when it's dark. And these stations are powered by a small solar panel and 2 100 amp hour batteries that get them through. When researchers visit these sites, ground time, as it were, is very short. So they typically fly to these weather stations, and then they have a very short window that may only be 3 or 4 hours at the most to do all the work they need to do. And so on the lower right, I included this picture of a checklist that they bring to all their sites about things that they need to do. So the work is extremely efficient and organized, and it was pretty impressive to watch from somebody who's been driving to my field sites for nearly 20 years. So we have something to learn there. The picture on the top right is a Met station on top of a glacier. I did not know that we had that until I went there, so that was pretty cool. A little bit about our telemetry network before I wrap up here. Our design is a little bit antiquated in a way. We have these Iridium satellite nodes that get the data out. Iridium is the only technology that works at the poles. Internally, we have Campbell Scientific radio, serial radios. We have stream gauges as well as lake-based under ice measurement stations. The stream gauges are only streaming while the streams are flowing, of course. And then this is all managed by Campbell LoggerNet server at the University of New Mexico, and the data are stored in Google Drive where they are then visualized on the website. And so this is just a map of part of our network. So those little squares are all different stations that are talking to a repeater on top of a mountain that sends the data out to UNM. And so we have these near real-time visualizations on our website of every station, and this is just an example of what those look like. And I'll get back to that in this slide after next. But some of our challenges right now are that we have this old technology. A lot of our data loggers are Campbell Scientific CR10s and 10Xs, and if you are familiar with that, you know that these are no longer being supported. We have just a lot of old equipment that needs to be replaced. We don't have a lot of expertise on the ground. It's difficult to get to these sites, and everything is expensive and complicated and slow in Antarctica. But in terms of visualization, we are trying to move forward. So we have this more immediate challenge that Joe alluded to earlier. I mean, data just really isn't useful unless we can see it and look at it. In a place like Antarctica, it's really nice to be able to show that off as well as to look at it. So I have a couple of RU students working with me for the next few months who are here at this meeting. If you have a chance to talk to them, please do. We are working together on developing an R Shiny app, which will be an interactive dashboard to our data. And we would like to have lots of different features. This Hubbard Brook LTER has done something similar, and so we like that. Other people are doing that too, and I'm just gonna wrap this up because we're almost out of time. And then this is an idea I had. So New York Times has been doing this thing where they've been plotting the last year's data with the historical average, and I think that would be kind of a fun thing for us to do with our visualization. And I would be interested maybe in other conversations at this meeting, hearing your ideas on how we can make this more compelling. And with that, I just want to thank our various funding agencies and logistics support. And we probably don't have time for questions, but I would love to talk to you guys about this later on this week. Thank you.
Okay, maybe we have time for one question while we switch over to the last talk. Uh-oh, maybe it is cursed. One question from Martha.
Renee, thanks for that great talk. Does your group look at or analyze any of the biological specimens at your camp, or do you send them back to McMurdo, or does it vary with your question? Or?
So all the nematodes and rotifers and things of that nature, diatoms, a lot of that is examined at McMurdo, either at the camp or in town. But there's a lot of DNA that's being collected, and that's obviously happening here in the States. So a lot of samples get shipped back to the States for post-processing.
Okay, finally, thank sticking around. We have Connor Scully Allison from the University of Vaderino. He's been our student fellow in the cluster for this last year. He's done a great job. He's on his way to a PhD at U of A, so hopefully he'll stick around the cluster for a little bit longer. But Connor, we'd be glad to have you, and thanks for your service.
Oh, thank you, Scotty. And I want to start off by thanking both the cluster and ESIP for an amazing experience. This is actually going to be my last ESIP meeting where I'm a fellow, and I just wanted to say it's a wonderful community. It's one of the best experiences I've had in my academic career thus far, so thank you. So yeah, I'm going to make this, so there's 5 front-end visualization libraries in 10 minutes. I have about 7, so let's see if we can do 5 and 5 so you can all get out to lunch on time. So first off, I'm just going to start off explain why am I doing this presentation, and it's because we're talking about time series data and some of the unique problems that are associated with visualizing time series data. You guys have data, you want to get it out there, so you need to think about what specific solutions will work for your data. Some specific problems I just want to go over with time series data that I have here is that it's very dense, especially when working with front-end and web technologies. You have tens of thousands to millions of data points. Processing those data points and visualizing them is going to cause you a lot of lag and slowdown. You have this problem of scalability and interactivity. Again, you're going to experience a lot of lag whenever you're trying to zoom in and pan around with these millions of data points being rendered on the front end. Also, in my particular case, I work with QA/QC. I want to accommodate granular metadata into my visualizations, make the colors look pretty and reflect meaningful information. And so it was very important to find libraries that work for accommodating that other information. So the first one that I'm working with is D3JS. I have here that's the king of front-end visualization libraries. It's actually just probably one of the most ubiquitous, but it's actually quite good. It's used by Square, New York Times, like Renee's photo there that was probably rendered with D3JS, Plotly, and Trifacta. And it uses a lot of native functionality, which means it's going to work for almost any web browser you have out there, which is pretty good. The important thing to wonder though is, will it work for you? And the language is JavaScript. It's kind of vanilla JavaScript. So if you consider yourself at least experienced with JavaScript, and more specifically, if you're working with something like jQuery a lot, you would be very well suited to start working with D3JS. Probably the biggest drawback of D3JS, however, is that it's fully customizable, which means you can do anything with it, but you have to rebuild it from the ground up just about every time. And that can be very frustrating sometimes, especially when you just want to build a graph and plunk it down. The next visualization library I have here is one called Victory. If anyone here is familiar with React, or if you're building a React application, this is an excellent charting library for that. It's simple and easy to set up, and it has those predefined graphs, so you're not spending a lot of time setting up charts like you are with D3 usually. And it's used by a number of pretty prominent companies. You see right here, 538, that's probably one of my favorite companies that does visualization out there. I could just stare at their graphs all day. For the question of, well, will it work for you? Well, for one, it uses JavaScript and kind of TypeScript, and then it also uses React. So you have to know React to start working with it. And it puts you kind of in this front-end dependency hell I put here. This happens a lot whenever you're building like more complex web applications. You're just downloading libraries upon libraries and building them all up together so that you have this really bloated application. And that can cause problems, but again, it's a lot easier to use than say something like D3. And then, like I say here, it's not really optimized for large data sets. However, they provide a lot of instruction on how to make it work with large data sets. And specifically, they have documentation on how to work with time series data. So it's very easy to set up for that type. Bokeh is my next one. This is, I think I'm pronouncing it correctly, Bokeh. It's a Python library. I say here that it's back end, front end. It's actually something that is processed on the back end because it's made in Python, but it's served down as like sort of a complete little HTML file. There's also other ways to serve down JSON information and embed it in applications. If you're familiar with Python, this can be a very good option, I would say, and it's very efficient compared to the prior two libraries because you don't have that problem of doing all the processing on the front end, which can cause a lot of slowdown, especially when you don't know the deployment environment. Onto whether it'll work for you. Well, it's Python, so if you know Python, that is probably a good option to choose. And it's very easy to set up plots, again, compared to something like D3JS. However, it can get a little complex. You have to start to understand how you're going to deploy it, setting up servers, and then dealing with that RESTful architecture of passing down an entire visualization or maybe some of the data that will render the visualization. All right, we're almost through. Renee actually gave me the idea for this one of Shiny. I'd never actually even heard of it before, but it's an RStudio library for making interactive web apps. And it's really great because it makes these full-on visualizations and dashboards, and you can just pass that down whole hog to the user, which is great. And I would say it's very similar to Bokeh because it does the processing on the back end with a back end language, but just pushes that to the front end. As for whether it'll work for you, well, the languages are. I would say that's great for scientists. It's a commonly used language. It's easy to integrate with existing research. So you just attach this little visualization component to the back of your normal data processing pipeline, and you'll be good to go. But what that also means is that you're kind of locked in to R. You have to use R for serving that data down, and it's very hard to embed. The recommendation that I found online for embedding, if you already have an existing website, is iframes, which for many reasons can cause a lot of problems. And then for maintenance and evolution, it can be good if it stays in the hand of environmental scientists, but if for some reason your project grows a lot and they have a front-end guy that's starting to work with it, they may not know R, and they may have some onboarding that will take. Finally, this is not actually a visualization library. It's a library that helps, called Crossfilter. It helps with managing large data sets with a JavaScript and JavaScript on the front end. So like Victory and D3JS, they will benefit from this one. And it basically helps you filter, map, and reduce client-side data sets. That's up to millions to tens of millions of points of data. And if you don't have something like this, it's actually extremely necessary because you'll see a lot of slowdown, a lot of lag when you're working with more than 10,000 data points. And you need something that starts to manage that for you for your user experience. I'm not going to talk about how it compares. And yeah, that's pretty much my presentation. How did I do? I got 7. Okay. Thanks, guys.
Thanks so much. Looks like maybe this thing's dead.
Here.
We have just a couple minutes. If Renee, if you have anything you want to bring up as far as cluster organization this next year, we wanted to open the floor to folks for suggestions on topics that you'd like to see the cluster focus on, try to bring in speakers for, things like that. So this last year, we've had LoRaWAN come up. We've had some of these QA, QC, near real-time, viz, and interactive applications come up. These seem to be topics that you all are interested in, but we also want to just hear from you with just a couple minutes that we have left. If you've got a suggestion we can bring in, we can just write it down. This thing's dead, so I'm just going to walk over and repeat the question.
So my question actually comes out of Joseph's talk, and that is something that I believe that the CNV really needs to focus on is if you think about how James and Martha designed their study that was specific to their study. Joseph showed how if you can do an average of 20 points, you can come up and get rid of a lot of noise. And then also adding in images of the ebb and flow of the stream adds in a lot more information. Now, both of these build stuff that is very specific to their use cases, but I can envision a different scientific field if we wanted to use the data somewhere else, or someone else wants to use that data. That noise is actually very important, and seeing that noise with the new images is very important. So possibly the community can start looking at when do you not remove data, when do you not edge process, and what is the optimal thing so that sciences that we don't even envision yet can say, oh wow, look at that. That noise is my new mosaic.
Okay, so for the online listeners and recording, the topic is capturing raw data, retaining the raw data such that the noise may be analyzed for potential uses in the future, and then examining those noises with other sensory sources, so cameras and images and this sort of thing, is a topic for us to talk about. And given what we've seen with, like, for example, the UNAVCO GPS data set and reconstructing rainfall at continental scales, that's one example of using noise. So I think that is a topic that we should bring up when we talk about, when we edge process, how do we retain some aspect of the raw data such that the data can be leveraged for things later. So I think, does that pretty much cover it? Perfect. Okay, James.
So I just wanted to put in a plug for a thing to talk about, is to talk about the open source hardware community. We talk a lot about open source software, but open source hardware is a thing that kind of took me by surprise, because I thought that's almost nonsensical. But it turns out there's a really strong culture that's doing this, and they're producing devices that Dan and I have been, Dan and Martha and I have been messing around with, that are dirt cheap and really capable. We're talking about things that are $1, $2, that are impacting the same space that the Camel folks were working in, where the things cost much more for it.
Okay, so open source inexpensive hardware matched with the software libraries that we're seeing is another topic that we could probably spend a lot of time on. I'll come back to you. Philemon, I think I saw your hand go up.
Yes, I will just try to shout. It was nice to hear that, efforts are made for QA/QC and efforts are being made to better utilize the data. But I think I failed to hear any efforts made to better document the sensors themselves. Are there any efforts that are out there that better describes the sensors that are being used, validation processes, and then, even journal the maintenance of those sensors, such as the application of sensor ML2? I have not heard any from any of the speakers with regards to documenting the sensors themselves. Other than the LoRa thing, I think there was an effort to list some specifications there, but there must be a better way of describing all these things.
Yeah, so quality assurance is definitely a topic that we talk about. XDomes, which I think you're affiliated with, is one aspect of this cluster that's working on that. It's something that we have to keep in the forefront, is that quality assurance. And Colin, I think, had a response to that.
Library of existing equipment that has the specs of those various pieces of instrumentation, what is its tolerance ranges, power output, or usage, et cetera, that would be essentially a community managed library of JSON specs. So that if you're saying, hey, I have a station out here, I have 14 sensors on it, it's this one, and now you know the ranges and tolerances of those various instrumentation. It gives you a first cut at doing some initial quality control.
Yep. And you're still at Eel River CZO, right? So you guys have been running a really nice quality assurance capture application for a while, as I recall, and you're on my list of people to bring in and demonstrate that. I'm assuming it's evolved. Let's see. I'm gonna go to one more, and then we'll adjourn because folks are hungry. Thank you everyone for coming. Thanks for sticking around. We hope you enjoyed it. So.
We need to document practices, methods, best practices. We need some form of repository or capability to access them rapidly.
Okay, so common repository for quality assurance is what we're talking about. Yes. No?
It's broader than that.
Okay.
Because it's how things are done.
Okay. Yeah, and you'll find it, and this is something that our 2014 edition best practices, where we covered many of these topics, and some of us in the room wrote chapters on this. That's a wiki. It's ready to be added to. So we've done snapshotting of the PDF, but that's an open document. And as these technologies evolve, please get involved. Please go on the wiki and contribute to that. And then if you make a significant addition, email the list and let us all know. And we can do annual snapshots as people update this, but I think it was Corinna and Dawn's intention that that document live on and grow as the technology and awareness changes. So please feel free to jump in and contribute to that. One more from Joseph.
Just real quick, you know, in this time of cheap sensors, inexpensive sensors, not cheap, inexpensive sensors, I think for the QA part, serial number tracking is super important. You know, in the optical world, an optical probe and the same optical probe are going to have differences, right? So when we look to revisit sites and put the instruments back out, maybe a new sensor is there, so time series of serial numbers.
Yep. Yeah. And I think we allude to that in the best practices, but the tools to do that, I think, are what the community is still wrestling with. And I think that that's something that we can continue to address as a community going forward. So in the interest of time and all of your patience, thank you for staying over. I think this was a really interesting set of talks. I was fascinated by everything. And thank you very much to all of the speakers for coming. So one more for the speakers. We'll see everyone online. We'll see you on the monthly calls. Please check into the email list and have a great rest of the meeting.